Hello everyone, welcome back to another video for the series, and today I would like to prove Desargues Theorem. I think this doesn't appear a lot in middle school division Olympiads, but rather in high school division. But I think it's really a powerful geometric tool, so that's why I wanted to introduce it to everyone, and please note that the proof and the definition that I'm going to provide from now on is not like that formal, because the definition and the proof are correct, and that's how most people understand this theorem. However, the reason why I will not provide I cannot, and also I will not provide a rigorous and formal definition and proof, because I think it's just harder to understand this theorem. So Desargues theorem states that two triangles ABC and A prime B prime C prime are axially perspective if and only if they are usually they write it, no, I don't think it really matters, centrally perspective. If and only if they are, so what this means is that actually perspective just means that when we extend our corresponding sides, and then their intersections are collinear. So this is if the intersection of extended side lengths are collinear. This one is if the line that connects to corresponding points, if the three lines that connects to corresponding points concur. So I think it's totally fine if you don't understand this definition right now. It's quite of a formal definition, I would say, but what this means is that I will just visually explain it. So let's say we have a triangle A, B, and C, and now we have a projector. So we have a light source, and that's P. And how should we? I'm thinking right now. Maybe like this. Oops. Oh. So yes, and this is A prime, B prime, and C prime. So what this means is that, okay, let's consider a light source P, and we shine the light to the triangle ABC, and this is the result that we get, somewhat like the shadow or Like this is A prime, B prime, and C prime are the outcome, and we say these two lengths are corresponding to each other. These two lengths, they correspond to each other, and BC and B prime, C prime, they correspond to each other. And similarly, the same applies for the points. Now, what the Desargues theorem states that is that, okay, if ABC and A prime, B prime, C prime are centrally perspective from point P, then they are also axially perspective. Meaning, let's connect. Oh, I'll use different color. Why can't I draw a straight line? This is our first one, this point. We have AB, BC. So we have, oops, this one. And this point. No, that's not good. This point. And the last one, which is AC. My example was bad, but it's fine. Okay. This is not like a great example. Okay, so let's assume that they meet at this point. Now, or like they meet at this point, like here somewhere. Then these 3 points are collinear, like this. They're collinear. Oh, you can trust me. So that's what the Desargues theorem is saying. The same applies for the converse. So if they're like triangle ABC, A prime, B prime, C prime are actually perspective, which means this line exists. I think this is called the axis of perspectivity, and this is the center of perspectivity. I think that's the terminology. I'm not sure. Please, if I'm wrong, please write in the comment below. Then these two triangles are centrally perspective from point P. So that's basically what the theorem is saying. And now we want to prove it. Actually, proving is quite easy. I mean, it's not like that easy, but we can use Menelaus theorem 3 times, and that will just simply lead us to the answer. However, let's define Menelaus theorem before that. So before we start our proof, let's consider a Menelaus theorem. So I think most of you might know that. So like if we have something like this, and we have triangle ABC, and like usually they use PQR, so then we know that. I will just name these B, CD, wait, EF. Then usually we define we usually know that times this time that A over B equals 1. I think this is like the most famous form of Menelaus theorem. However, this is not like there are more cases than this, and that's why I quite want to like somewhat generalize it. And let's say we have a triangle ABC, and we're going to extend the line. B AB, BC, and CA. We're going to extend them. Okay, let x, y, z be points such that x is in line AB, y is in line BC, and z is in line CA. Then, using cross ratio, we have XA times YB, YC. This should be right. I think so. Equals -1. And you might wonder why is it negative? That's simply because there are, like as I mentioned, there are more cases than the previous case. So we need to consider multiple diagrams, and this just simplifies everything. So it's like a signed ratio. So we actually have to use this form instead of the previous form to prove our theorem. And let's finally start our proof. So first, we want to prove that triangle ABC and triangle A prime B prime C prime are axially perspective if they are centrally perspective. Okay, so let's say I need a bigger place. So let's say we have triangle ABC. We have point P here. We already know that ABC, A prime, B prime, C prime, they are centrally perspective. Let's just say that this is P. Okay. Is this a great diagram or not? These two meet, these two meet, these two are so. Oh, I think this is a pretty nice diagram. So we have, oops. C prime, and let's connect them. So we have AB like this. Yes, and we have B prime, A prime. They meet at this point right here. Oh, I think my diagram is so good. Like, I tried to prove with a different diagram, but that was really hard to draw and LaTeX. So I should use this diagram from now on. Like, I don't want to use BC. That was not good. And we have it, I think, around here like this. Wait, I need to prove that They're collinear, but they don't look collinear. It's okay. Let's say that this is x, this is y, and this is z. Wait, where's my okay? This is point P. First of all, consider the triangle P B prime, no, P A prime B prime. So we're looking at so first of all we're looking at this triangle. We're looking at this, and then we're going to look at the line x b prime. Yes, I think that's a reasonable choice. So what we have here is this time, so using Menelaus, we know that times okay, I want to use so we're looking at this line right now, this one. Now if we consider them as this, and that, then we have this one in here, so this over that, and we have this one, A, B, C, so we have this one in here to here, so we have B, B prime over BP times we have, wait, what is this, A, you have this one, CA, so we have that and that. Okay, we have PA, I will say AP and AA prime. This is simply equal to 1, not negative 1 here, because as I mentioned, that was for signed. X B, this is B, right? Yeah. The next triangle that we're going to consider is triangle P B prime C prime, as you might have guessed, B prime C prime. So we're looking at this whole thing. For this one, we need to look at B prime C prime, right? B prime C prime. We're going to look at a different line. Maybe let's look at this one. So we have YB or YB. By Menelaus, we know that if A, B, C, then we have this over that, A, B, C, so we have B, Y, Y, C prime times we have this one, this over that, so BP over BB prime times we didn't do this one, right? So we have A, C, A, so we have C, C prime over CP equals 1. Now we have our last case, which is, as you might have guessed, triangle and PACA. So we have this one, and we're going to look at, which lines are we going to look at for this one? Should we look at this one, this line? This is ZC, right? So for this triangle, for this one, when we use Menelaus, But this time I want to like flip it. A, B, C. And what I mean by flipping is like reciprocating everything. So we have A, B, C. So A, but we do this one first. Times we didn't do A, B, C. So we have to do this one. AP A double prime times we did this side, we did that side, we didn't do this side yet. So we have A, B, C, and C up B, C. So we have CP and CC prime equals 1. Oh wait, I think I flipped it. Oh, yes, I flipped them. Sorry. We have CA, CA, AB. So we have B, AB. So we have this over. No, actually, never mind. I don't think we have to flip them. Like my previous proof actually flipped it, but I don't think that is quite necessary here because we have all we need right now. So we have everything that we need. A B, so we have AP. I mean AP times. You need to use this one. It's BC, right? So we have CP over CC prime equals 1. And now here, let's multiply this tree. So we have, if we multiply all of them, we cancel out these two, cancel out this two, we cancel out these two, this one, and this one, and that. So therefore, ZC prime over ZA prime equals 1. And does this look familiar? Does it look familiar from here? And yes, I think so. So let's consider the triangle A prime B prime C prime, which is right here. And points X, Y, and Z. You know that X is on AB, Y is on A prime B prime, and Y is on B prime C prime, and Z is on C prime A prime. And by so doing that we have actually, but there's one more condition here. X, Y, Z are collinear. Oh, I forgot about that condition. I'm sorry. By converse of Menelaus theorem, X, Y, Z are collinear. Thus, triangle and so if they do that, then this satisfies, so we know that. Okay, so if triangle ABC and A prime B prime C prime are in perspective from the point P, then we prove that X, Y, Z are collinear, which means then does A prime B prime C prime are axially perspective if they are centrally perspective. Yay! And we now have to prove the second part of the the theorem, Desargues theorem, which is triangle ABC and triangle A prime, B prime, C prime are centrally perspective if they are axially perspective. And actually, you know what? I really loved my diagram here. I want to copy and paste it. I just love it. Oh, no. Command C. We have here Command V. Nice. Nice, really nice. We have, okay. Good enough, I think. Actually, from here, we just need to consider a different triangle. I mean, what I mean by that is let's focus on, oops. Let's focus, oh no, let's focus on different triangle. And we're going to use the, we're going to use the same conclusion that we got. 5 more seconds, please. No. Okay. Okay. No. Why can't I erase? Oh, nice. I think everything's clean, right? Okay, so oh no, actually I would like to erase this one. So we are going to use the same constructor method, A, B, C, and A for these two, but we don't know if A prime if it means a P. We just don't know that. However, we know that these 3 points are collinear. So that's the thing, one fact that we know. So what we're going to do here is we're going to consider I forgot which triangle was it. I think it was these two. I'm not sure. No, I mean, if this is not right, we can prove it using other triangles. So yeah, let's consider these 2 triangles. We know that. First of all, we know that. We know what? Okay, so if you have these 2 triangles, we're going to connect. No, actually, I don't think this is the right triangle. Yes, I think we have to use different triangle. I'm not sure if this is right. Wait, this one? No, wait, you know what? I think yeah, I'm sorry. I did review before making this video, but I'm like suddenly confused if I'm using the wrong triangle. Wait. This one? If we use these 3 triangles, we have this one. No, this is not right. However, if you use these 2, I actually don't have the proof with me right now, so I need to figure it out if this is right or wrong. I'm really sorry. Let's think about it one more time. So I'm pretty sure we need to use Menelaus here. I mean, like the previous result that we got. Okay. If we use these 2 triangles, what happens if you use those two triangles? This one and this one. Connecting that, we get these two are correspond. No, that doesn't work. However, if you use these two triangles, you know they meet at x. These also meet from x. However, I'm not sure if. Oh wait, no, actually, you know what? I think this is right. It was just that my drawing was not clear enough. Okay, so let's use this triangle. Okay, we know that these two points, if we draw a line that connects B and C, they meet at Y. These two, they meet at Y. These two, they indeed meet at Y. I mean, it doesn't look like it, but it is because we assume that they are already axially perspective. So we know that, therefore, we know that B prime X and C prime Z are in perspective from point Y. And here, actually we're done here. And the reason why we're done is because, okay, we know that this is a center of perspective, and we're going to use the result that we got from like here, so that we don't have to do every single thing again. Okay. We know that by construction, these two lines, they meet so we know that these two, they meet at P. And also using so what is P? Connecting these two, we get P. Okay, we already know that Y is the center of the point. I mean, center of perspective. Now, okay, so we just need to prove that B prime and C, let's assume that when we connect B prime and C prime, we get P. Now we just need to assume that P is on the line A and A prime. In other words, we just need to show that P, A prime are collinear. Then you're just done, right? And that's actually really simple. And the reason is because, okay, let's look at our previous, our first half. We know that, if P is the point of perspective of ABC, if ABC and A prime, B prime, C prime are in perspective of point P, from point P, then we know that Y, X, and Z, they're collinear. And now notice that they are just the same thing. So if Y is if X B prime B and the Z C prime C, if they are in perspective from point Y, then we know that they are also axially perspective. That's what we proved, right? That's what we proved. So meaning, if you connect them, this one, this point, which is same as P, this one, and are they corresponding? Yes, that they are corresponding. Which is A, which is by construction, it is defined as A. Oops. This is A prime. and we, oh my goodness, a prime here. In other words, they are collinear. This line is collinear. Um, therefore, a prime p are collinear, and p equals a prime, b prime, and c prime. And we proved our Desargues theorem. To be honest, like, I'm not like, I didn't solve much practice problem for this theorem. I just, so for the past 2 days, past, yes, 2 days, including today. So like yesterday and today, I only studied this theorem, and I was able to prove it and also learn the theorem. This theorem actually uses projective geometry, but like, I'm not an expert in projective geometry, and also I don't think like much knowledge is quite needed for this theorem, even though this is a theorem from projective geometry. I think like the idea of using Menelaus 3 times was really great here, and so like if we have a problem that we can solve using this Desargues theorem, then I'm pretty sure we can solve it using Menelaus too, because that's how we prove Desargues theorem. So it would be more steps, but if you use Menelaus theorem, but if you use the Desargues theorem, then we can do all of them at once. Because I could not apply this theorem, like this knowledge yet, maybe tomorrow I will come back with another video, another problem that is about Desargues theorem. And I apologize for not like being really clear in my proofs, because as I mentioned, I don't have a proof right now. Like right next to me, I don't have it, and also the reason why I didn't prepare a proof right next to me right now is because I think copy and pasting is not like learning for me. So I just wanted to try and prove it on my own, and that's why I was confused here and there, but I think the proof is correct. So if you have any other concerns or questions, or if you think the proof is like I made a mistake in the proof, please feel free to let us know in the comments below. And thank you, and see you tomorrow. Bye.